All right, so this video is going to be on the halogenation of alkanes. And so first I really just wanted to kind of show you what you did last semester. Right, we got a chloroethane hydroxide. We make an alcohol, right? We can do an elimination reaction too, but the point is we used a chloroalkane and we did a substitution reaction. And then we can take that alcohol and make a variety of other things, right? So this is a very useful synthetic tool. This starting material, however, was given to us every time last semester. Now we got to figure out how to make it, right? And so the best way to make it, or a very easy way to make it, is um, a radical reaction, right? And so we know we have to start with ethane, or I'm telling you that right now at least. And if we do a radical substitution reaction, we can add a chlorine, right? So let's take a look at how this will really work out for us. All right, so this can be done, like we said in a previous video, using light or heat, right? So that's going to introduce or create the formation of that radical. And what I want to do now is kind of go over just use methane as an example of how we might create a halogenated species. So we have methane, and we can introduce light or heat. And if we had methane in the presence of, I missed it, X2, which X2 is the chlorine or bromine. It's not going to be iodine or fluorine, okay? So fluorine and iodine, iodine reacts much too slowly, and fluorine is too crazy. It's like gnarly, and I'll show you why later, okay? Or I'll prove it to you with some bond association energies and enthalpy. So after we add one halogen, we create this chloroalkane, and then we have a dichloroalkane, and then we can add another one. We have that trichloroalkane, and then finally we get that tetrasubstituted alkane, right? And so this is pretty much the process of chlorinating an alkane, right? That's more or less how it's done. Obviously, there are a lot of nuances associated with this particular reaction, the mechanism, and how to make things work in your favor. But remember that X2, the presence of heat or light, breaks up into X dot, two of them, right? And so what it does first is abstracts a hydrogen atom, making HX for each of those reactions, right? And so that's exactly why, like, one of the reasons why you don't want to do it with fluorine is because you're going to make a bunch of HF. HF, as you know, probably from Breaking Bad, is not good, right? Even though Breaking Bad's experience with HF was not accurate at all, it's still not a fun thing to mess around with. So, a note here: when asked to draw the products of halogenation of an alkane, what you want to do is draw the monosubstituted product. Okay, so unless it specifies otherwise. Okay, so what I mean by that is remove only one hydrogen atom and replace it with an X atom. Okay, and so that's it. That's what you want to draw when you're asked to draw the product of a halogenation of an alkane. Okay. All right, so let's take a look at what I mean. Obviously, with the words above. So draw the products of halogenation of this alkane, right? And so we've got cyclohexane with bromine, elemental bromine in the presence of light or heat. And what are we going to get? Well, we are going to get bromocyclohexane as well as HBr. Okay, so that's because we want to draw the monohalogenated product. Even though we can technically form a much more substituted product, the question is, unless otherwise specified, it only wants you to draw the mono substituted product. Okay, so if we're going to do this with propane and chlorine, we will form multiple species, right? So we can form a 1-chloropropane or the 2-chloropropane, and it's really helpful to know your nomenclature, because then you're able to differentiate between these two species right here. And so you can say that the top species and the bottom species are both 1-chloropropane. Therefore, they are the same and they are not constitutional isomers, for example, right? Which is what we want to practice, y'all. We'll talk about practice. So let's see what it looked like. Draw all constitutional isomers, right? Like these guys, right? These will actually form in a 1-to-1 ratio, which we'll get into later because that's weird, right? And that's contrary to what we know about carbocations. But let's say we want to form all of those monochlorination products, and we want to make sure they're different though, right? So again, nomenclature is really important. If we put a chlorine on any of these basically corners of that square, which is the cyclobutane, they'll be the same, right? And so that's what we have to know this. And if you know your nomenclature, it's really easy to do that. And so that's what we're going to do kind of to help us move forward quickly, right? So do these on your own, of course, just like before, and then like pause the video and then see if they match mine. That's the only one for the chlorocyclobutane. There's 6 carbons in this particular alkane, and those I kind of like show a squared circle triangle to show you which ones are similar, which ones are different. And then that way we know quickly how many different isomers there are, right? So there's only 3 because there's a square, a circle, and a triangle, and that's it. All the other ones are the same. All right, so now this particular guy right here, we've only got 2 sites that you can substitute to get a different product, and that's these are those 2 guys right here, and that's pretty much it. Again, it helps if you can identify the names of the species to quickly move on and not write 2 of the same thing, but otherwise you can just look at it and see if it's the same thing. All right, so the mechanism of halogenation. So this is that good stuff. Well, I do want to give you a little reminder. So how to form radicals. We need H nu delta, and then the ROOR, that's the peroxide, and then how to inhibit a radical reaction. We introduced oxygen as a source, but we also had our scavengers, so like our pi bonds in vitamin E or fats and things like that, the antioxidants, right? A little fun fact for you, but it's also really useful in kind of determining if a mechanism is a radical or a carbocation intermediate, right? So there's no rearrangements, right? That's super useful. If it doesn't rearrange, and it would have in a carbocation, if it had a carbocation intermediate, then it's not a carbocation intermediate. It's going to be a radical mechanism, and that's super useful. Okay, so we have 3 steps to a radical halogenation process. Okay, that's going to be initiation, propagation, as well as termination. Okay, and I think the names kind of tell you more or less what they do, but it is important that you kind of understand the definition of these, and I'm going to introduce them the basic definition right now. So that starts by forming a radical. That's the initiation process, right? The propagation is basically the reaction proceeds and then it continues. And then termination is when the reaction is finished or quenched. Okay, it's stopped basically. And so now I want to go over each individual step and show you the mechanisms associated with those. They're going to be specific, but you need to be able to generalize them and identify an initiation step and propagation and termination. Okay. And then the definitions will kind of get a little bit more wordy so this time around, but we'll also have pictures to go along with it. So it'll be easier. Let's say we had this cyclopentane plus chlorine in light, and we want to draw the chlorocyclopentane product, right? So what's the mechanism for this? Well, first there has to be an initiation step, okay? Now you have chlorine, elemental chlorine, looks like this. When it undergoes homolytic cleavage, you form 2 chlorine dots, two chlorine radicals, right? And that's the initiation step. The reaction has been initiated. It starts by forming a radical, right? So something has to undergo homolytic cleavage. Now it could be elemental chlorine, for example, and then it forms two radicals because it was homolytic cleavage, right? So I'll give you a couple other examples of some common radical initiators. There's definitely more than just this, but I'll introduce these ones because they're in the chapter. So it doesn't have to be just chlorine or just bromine or whatever, right? Like it could be a bunch of other things, but here's the bromine example right here, right? We form two Br dots. We have seen like hydrogen peroxide, for example, we've got two HO dots. And then we also have, you've heard of CFCs, right? CFC, this is an example of a CFC, CFCl3. In the presence of a light, it forms this CFCl2 dot, as well as a chlorine radical, right? This is why the breakdown of the ozone occurs. But basically, this is just some sigma bonds undergoing homolytic cleavage and forming two radicals, right? And so, again, those are just a few, and those are some that we'll become very familiar with. And but I just wanted to use some other examples to help you identify the definition of initiation. Okay, so now what we've got is the propagation step. So once we've formed that chlorine radical, we want to use that chlorine radical, right? And we want to use it to make chlorocyclopentane in this case. So cyclopentane has a hydrogen that may be abstracted with that chlorine radical, and the mechanism looks like this with the fishhook arrows. And what happens in the propagation step is it removes a hydrogen atom and forms HCl in this case because we're using a chlorine radical, and then it forms a new cyclopentane radical. Okay, so that's the theme for propagation. You have a radical and it reacts with a species and it forms a new radical as well as a sigma bond, but like I don't really care. I mean that it does form as well. So radical reacts with something to form a new radical, okay? And then like whisper, also a sigma bond. And all right, so the thing about this is that cyclopentane radical can move on with its life and react with other things that are in you always gotta envision this in like a flask or like a beaker or something, right? And so it's in a vessel of some sort and there's a bunch of stuff mixed together. And so there's still more chlorine around, and that cyclopentane radical reacts with that chlorine to form chlorocyclopentane as well as another chlorine radical. So now that chlorine radical can just go back up to the top of this cycle and form or react with another cyclopentane molecule, and then forms a cyclopentane radical, which then reacts with more chlorine, which then forms more chlorocyclopentane product, and the cycle continues. And that's what's super dope about propagation. So that's what the definition is. It's really just the radical reacting with some species to form a new sigma bond and a new radical, and then boom, boom, boom. Okay. Now, termination is the end of this reaction. This is when it gets quenched, right? And so there are a variety of ways to quench a reaction, but the gist of it is, in this case, going to be two radical species that are present coming together. Okay, so for example, if you had two chlorine radicals or two cyclopentane radicals or one of each, they would come together with each of their unpaired electrons and form a neutral species that with a new sigma bond. Okay, and it doesn't matter if the product is desired or not, it will form a neutral species, and there's no more radicals present, right? And so that's why this is a termination step, because if this happens in a mass amounts, because obviously there's not just one radical floating around, right? there's a certain population density of chlorine radicals present, or cyclopentane radicals. And once those two radicals combine to form a stable compound, then the reaction is quenched, though. And if you have a large proportion of those radicals coming together to do that, then essentially the reaction slows down and then eventually stops. And so it's all about statistics, right? The more radicals you have present, the more stuff that can go on. I mean like stuff, because radicals can either do what you want them to do or not. They can wreak havoc or make the product that you desire, right? And so that's just how it is. All right. So there was the initiation step, right? And then the propagation step, and then we had the termination step. Okay. So it's important that we know how to identify these. So the initiation step basically just formed two radicals from a sigma bond. And then the propagation step took one of those radicals, created a new radical and a new sigma bond, right? So this is the new sigma bonds right here. Circle those bad boys in green. And then we formed radicals. It's important to form new radicals to allow this cycle to continue. And then we have the termination step, where we have two radicals coming together to form two neutral species with a new sigma bonds. And that's pretty much it for the mechanism, right? Cool. All right, so this right here, this is some special stuff for you. Okay, so your book does talk about it, but I'm gonna bring up just some little extra points. Like they mention fluorine sucks and iodine sucks in halogenation, right? So what we're gonna do is use energy of halogenation of ethane to kind of show us why that is. So in terms of like enthalpy, right? Because you could hypothesize a variety of reasons why fluorine and iodine wouldn't be very good. But in terms of energy, we're going to kind of go and prove that to ourselves. So what we're going to do first is kind of go into detail on the ethane reacting with chlorine to form chloroethane. Okay. And then after that, we're going to kind of go over bromine, iodine, and fluorine as the reactants. And then these are going to be all the products, right? So bromoethane, iodoethane, and fluoroethane with HBr, HI, and HF, right? And so I already told you HI and HF, or HF is gnarly, HI is a strong acid, right? So those are still the stuff when you're working with strong acids, the equipment you're working with can get easily corroded. And so maybe that's part of the reason why you might not want to do these reactions. But then there's also the fact that they're so slow and so fast with iodine and fluorine respectively, okay? And what we're going to be using is chapter 6 bond association energies. If you're using Smith's 6th edition, that's page 231. If you're using something else, then look in the index for bond association energies. Super chill, easy to find. And we're going to we're going to kind of show why these basically chlorination and bromination are the only synthetically useful halogens to make alkyl halides, right? And I want to make sure that we know that we're only looking at just the propagation step, okay? And that's because that's all we really care about in terms of like the energy, because the propagation is where most of the energy is either produced or put into, because that's the bulk of the reaction that makes the product, right? So if we have a hydrogen being broken, a CH bond being broken in ethane, and then an HCl bond being formed in this propagation step, then that's the only thing we need to look up in the chart, the bond dissociation energies. So bonds broken. Remember, anytime you break a bond, you have to put energy in. If you're forming a bond, then it's releasing energy no matter what. Okay, so we have a positive 410 and a negative 431 for the bond formation and bonds broken in this case. And so, all right, so when we combine those two together, what we're going to get is negative 21 kilojoules per mole. Okay, so remember, this is a propagation step, right? So we aren't done yet, right? So we have the ethane radical that's going to react with elemental chlorine, and that's going to form chloroethane as well as another chlorine radical. Okay, so that's the final step in the propagation step to get to our final product. Okay, so The bonds broken in this case are going to be elemental chlorine. Bonds formed are chloroethane. And so we look at our chart and we find that that's positive 242 for bonds broken and negative 339 for bonds formed. Combine those two together. And what do you get? Give me a second. That should be 97 kilojoules per mole. Okay, so both of these processes are negative values, right? And so that means they're both exothermic, releasing energy. And so what we want to do is actually take a look at the energy diagram for this. So on the y-axis, we have energy. And then on the x-axis, we have the reaction coordinate, right? So we can start anywhere on this. That's our 0 point. And so in order to break the bonds, it's an exothermic or endothermic process. So it goes up 410 kilojoules, right? And then we release 431 kilojoules per mole, which means we go down past the 410 and then go a little bit further, right? 21 kilojoules below that. And so that's why this process right here is exothermic. Okay, and this is really important that you guys remember this because this isn't the first time this will come, this is the first time it's coming up, but it's not the last time. Okay, so the next step is the formation of that chloroethane, right, from the ethane radical, and that goes up 242 and then down 339. So again, that net process is exothermic itself as well, and so that's pretty much. So the reason why I'm going over this in such detail is because I want to zoom through the rest of the reactions, because I really do want to show you those, even though your book just kind of glazes over them. Okay, so we have minus 21 and minus 97 for that difference, and overall, if we combine those two together, what we get is minus 118 kilojoules per mole for the net process. And so this entire process again is exothermic, right? And we know just from reaction diagrams before that exothermic versus endothermic reaction, those have an effect on intermediate species, their transition states, yada, 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 right? And so just a little hint as to what we'll be looking into later. Now let's take a look at we're going to look at the bromine, the fluorine, and the iodine equivalent of this process. And so I want to go through it fast, but it's kind of difficult to go through fast, but it'll definitely be abbreviated from the chlorine addition. Okay, so we're going to have to look at our charts to get these reaction bond dissociation energies. And so the first step is going to be ethane losing a hydrogen atom, and the second step is going to be basically gaining a halogen, right? So I want to label these as, just real quick, because I'm going to sum up the energies in like basically 1 and 2, then 1 and 2 for iodine, 1 and 2 for fluorine, 1 and 2 for bromine, right? So here we go. So for ethane, it's 410 for all of them, okay? So 410, 410, 410, okay? So because we're always starting with ethane. All right, and so now the next step was the bonds formed, or sorry, the same step, but the number that we have to look up is the bonds formed. And now in this case, we're looking up HBr. Now, if you look in your chart, the HBr's value is 368, but its bonds formed, so it's negative 368. All right, and so we'll go ahead and record that down here and then take a look at the next step, which is the bonds broken for the step 2 process. The bonds broken is 192, and then we have, sorry, I gotta find it real quick. It's 285 for the formation of the bromoethane. Okay, so whoops, I made a boo-boo here. So, sorry, I was writing this information on the iodine section. So, we'll go ahead and convert this little portion into for bromine. Then we have for fluorine below, and then we'll go ahead and throw for iodine below that. My bad. Sorry about that. I started in the scheme above, and then I ended up just drawing it all in the numbers below. So basically, what we need to do is move on to the next step, right? So what we've got here is, I'm going to hammer through these real quick. For fluorine, it's negative 569. Let's look at iodine. It's minus 297. Okay, so now we need to look at the bonds broken for fluorine and iodine, right? So for elemental fluorine and elemental iodine. Okay, so take a look-see at our chart. That's a positive 159 for fluorine, positive 151 for iodine. Okay, and then we need to look at our bonds formed for the final halogenated product, right? And so for the fluoroethane, that is going to be, let's see, where you at? 448. And then 222. You want to make sure that you're not choosing the like fluoropropane or whatever. You need to make sure that it's the fluoroethane just to make sure, or double check your work, right? So, all right, and so now we basically want to look at how we kind of added these numbers up together. Shazam! Check it out. All right, so there's two numbers in each of these, and then there's a total, right? So positive 42 is basically the first step in that reaction. And so if we're drawing the curve, we would have an endothermic step, right? And then it's negative 93. So that next step is a exothermic reaction or exothermic process, and then overall is negative 50. So that gives us an overall negative or exothermic process, right? So that's what our curve would look like. And we should be able to do this for fluorine and iodine as well. Both of these processes are negative, and the final is negative 448 kilojoules per mole. Are you serious right now? That's crazy. That's why you don't want to do fluorine radical reactions, because shit gets wild. I'm gonna be real with you. Like, you don't want to mess with that. That's crazy. So gnarly stuff, forms gnarly products too. HF. Not about to have that displaced calcium in my bones and then ruin my day. Like, so hard. But iodine, you can see that first process is positive 113. That's an endothermic process. And then it goes down negative 71 with an overall positive 42 value. That's an endothermic process. You're putting energy in to make this iodine substitution happen. That's why it's not favorable. That's why it's hella slow. And negative 448 is wild. That's why it's violent and highly exothermic process. Okay, so it can get out of control too. If you have a highly exothermic process, that's just one step, right? Like, you're releasing 448 kilojoules per mole. And then let's say you did 2 moles, right? You got to double that. And then you do 3, like, it's just, yeah, that's why you don't want to do fluorine or iodine. But bromine, on the other hand, remember that chart right there, that reaction coordinate, or that diagram, because it's chill, it's endothermic process first, it's exothermic second step, overall exothermic process. That's highly favorable, and you'll see soon in another video why bromination is the best in the biz. All right, have fun.